so the easiest way to envision this mechanism is not the way it actually happens. Okay, this is another one that's a little bit misleading because it's really easy to just kind of like think about this happening with a general base in the active site here, deprotonating that hydrogen, the C2. The electrons moving down to make a double bond between C2 and C3, and hydroxide exiting, right? Here we've lost this hydrogen and this hydroxide, so it's ultimately a dehydration, creating a double bond, okay? That's absolutely the easiest way to think about it happening. However, there's an intermediate, and that intermediate is really the big driving force that allows deprotonation of that carbon. So the idea here is in the active site, you have some magnesiums positioned here. And that's important because that then draws electron density from this CH bond up towards the magnesium, and it makes that CH bond more reactive. Okay, so in the mechanism, instead of having an immediate dehydration, we go through an intermediate where we remove the proton and make this ene diol intermediate. Okay, so if we look here, I can zoom in here. I can't. What did I do? Okay, so if we look here, right, so we have the deprotonation we expect. That's this first step, deprotonating C2. But instead of first making the double bond between C2 and C3, resulting in the hydroxide leaving, instead the electrons flow up and make a double bond between C1 and C2. That's facilitated, that's allowed because of this nice positive density from these two magnesium ions. Okay, so the electrons are drawn towards those magnesiums. They're drawn towards this oxygen, and that makes this CH bond more reactive. It makes the deprotonation of a carbon more feasible. And then once we make this intermediate, we can then reverse it. The electrons flow back down to make the carboxylic acid. Our double bond moves from C1 to C2,3, and then ultimately at this point we can now have our hydroxide leave. And it notes here that it picks up a proton from this glutamic acid. Okay, so the overall process is what we expect. It's deprotonation of C2, hydroxide from C3 leaving to make this this phosphoenol intermediate, this phosphoenol product. Okay, but to make that CH bond on C2 more reactive, we have to go through this intermediate that involves pulling electrons towards that magnesium. Okay, and if you look in the active site, you can see everything you expect there, but I'm running a little bit long, so I'm going to skip this. And that brings us to our very last step, which involves the transfer of phosphate from phosphoenol pyruvate to ADP, creating our second equivalent of ATP, or really our fourth equivalent of ATP in glycolysis. Right? This is hopefully straightforward chemistry. The same idea with a binding cleft that allows the substrates to bind. The phosphate is transferred from phosphoenol pyruvate onto ADP because PEP has a higher phosphoryl transfer potential than ATP does, so it goes in the direction that we want. Remember glycolysis? The whole point is to create high energy phosphate compounds to make ATP. This is the second one. And also remember that the reason phosphoenol pyruvate is so high of a phosphoryl transfer potential is because as soon as we remove that phosphate, right, as soon as phosphate gets removed from C2, we now have the enol tautomer, and the enol tautomer is no longer trapped in the enol. The presence of the phosphate traps it in the enol. So once the phosphate is moved, you have this massively unstable enol, which can then tautomerize back to the keto form, pyruvate, and that tautomerization is very spontaneous. Okay, that's the really big driving force. All right, so those are the reactions of glycolysis. Does anybody have any questions about any of the mechanisms specifically, or anything you want to go over again before we kind of move on? All right, so we got about 20 or so more minutes to almost 30 minutes to talk about some ideas of regulation of flux through glycolysis, and then perhaps, if time allows, to start on gluconeogenesis. Okay? So somebody remind me, what does flux mean? This is something you should be able to define. What does flux mean? Change in what context? I think we're going on the wrong path. So flux is flow, right? Flow through a pathway. So think of flux being traffic, right? So you have all of these different roads, all of these different ways to get from Rock Hill to Charlotte, or Rock Hill to Columbia, or wherever the hell you're going, right? You have all these different pathways. Those streets correspond to different metabolic pathways, right? And as it might be most efficient to go down Cherry Road, get on I-77 and head north to Charlotte. But that also might not be the most efficient, right? There might be some blockage which backs things up. Flux down that pathway, flow down that pathway is stopped, so metabolites divert in other directions. That's the big idea here. That's the idea of regulation of metabolic flux, and that's generally the idea of flux, is it's all about moving things down one pathway until we no longer need to, and then they get deferred down different ways, right? And that deferment could be storing energy, it could be making other molecules, right? Whatever the cell needs at that time, okay? So for cells, for organisms, flux really boils down to the energy charge of the cell. Remember that idea of energy charge was basically the relative amounts of ATP, ADP, and AMP. And we defined this idea of energy charge based on those relative concentrations, okay? So cells are really, really good at recognizing those relative concentrations, okay? And in glycolysis, there are three key regulatory enzymes, and they're the ones you expect. They're the ones that are irreversible. They're hexokinase, phosphofructokinase, and pyruvate kinase. Those are the three key regulatory steps, okay? And as it turns out, phosphofructokinase is by far the most important one, by far. It is inhibited by ATP, which hopefully makes sense. A buildup of energy stops making more energy. A high energy charge of the cell means we don't need more energy, so let's turn off glycolysis. Let's slow down flux through glycolysis. The reverse is true with a buildup of AMP. A buildup of AMP means a depletion of ATP. So that means we have a low energy charge, we need more energy, let's ramp up flux through glycolysis. So a low energy charge, we have a high flux through glycolysis. A low energy charge, we have, a high energy charge, we have a low flux through glycolysis. Okay? And it's interesting why AMP instead of ATP or instead of ADP, right? Because it may seem logical to think that ADP would be an important allosteric inhibitor as well. But as it turns out, it usually isn't. And the reason for that is that when ATP starts becoming depleted, one strategy that cells have of quickly getting more ATP is converting the ADP into ATP, right? There's this enzyme, adenylate kinase, which takes two equivalents of ADP and creates ATP and AMP. So if we were using ADP as an indicator of low energy charge, that'd be a problem because the ADP gets depleted to make more ATP. But upon depletion of ADP, we get a lot more AMP. So a low cellular concentration of ATP is very much signaled by a buildup of AMP. So AMP is by far the more important signal that we need more energy. Okay? Think about a map of kind of how this works in general, right? So on the right here, we have a cell at rest. We have a cell that does not need energy, that is hanging out, nothing's really needed. And on the left, on the right, for you guys, we have a cell that is actively consuming energy. So we need to have more energy, right? At rest, we have a buildup of ATP and a depletion of AMP. So we have a high energy charge. This high energy charge is recognized by pyruvate kinase and phosphofructokinase. Okay? It inhibits them. It somehow impacts those enzymes in a way that it inhibits activity of those enzymes. In addition, so inhibited PFK means a buildup of phosphofructokinase, which means a buildup of glucose 6-phosphate, and a buildup of glucose 6-phosphate is actively product inhibition of hexokinase. Right, remember, hexokinase is the enzyme that converts glucose to glucose 6-phosphate. It's the committed step. It's subject to product inhibition. Basically, the product is locked in the active site, and it just doesn't leave, so substrate can't bind. Okay, so a buildup of ATP slows down PFK, which results in building up glucose 6-phosphate, which inhibits hexokinase. Ultimately, we're building up glucose 6-phosphate, and that's an important signal for other pathways to say, let's use this glucose 6-phosphate to do other things. One of the things we can use it for is to make glycogen to store energy. Okay, so this is something that we'll see over and over here. A buildup of ATP means we have extra energy in the cell. Let's store it for when we need it. And one way of doing that is to convert sugars to glycogen. The opposite is true when we need energy. ATP levels are depleted, AMP levels are high, we have a low cellular energy charge. So this increased AMP concentration activates phosphofructokinase. Okay? That then leads to a buildup of fructose 1,6-bisphosphatase, which then will then push forward the rest of the reactions that are in equilibrium. In addition, we have this feed-forward stimulation, right? As opposed to feedback inhibition, feed-forward stimulation, increased levels of fructose 1,6-bisphosphate will activate pyruvate kinase. Okay, pyruvate kinase, of course, is the enzyme that converts PEP to pyruvate, making more energy, pushing things forward. Okay, so it all makes sense. Thinking about phosphofructokinase, PFK. Okay, so what we're looking at here is a Michaelis-Menten curve that I've intentionally put on a log scale on the x-axis so that we can see the differences a lot more clearly. Okay, but the important thing to recognize is that this dashed line right here, this represents 50% activity. And remember, when activity is at 50%, the concentration of substrate at that point is the Km, right? So these points right here correspond to basically the dissociation constant. And we know that the larger the dissociation constant, the weaker binding. The smaller the dissociation constant, the tighter binding. So the idea here is that the white line represents something that does not have an activator or an inhibitor, the base enzyme activity. Adding the activator, AMP, we see that it still gets to the same Vmax. This green line still has the same Vmax. Adding an inhibitor, this red line still has the same Vmax. But we see a dramatic change in the Michaelis constant, which means the way that these activators or inhibitors work is not by impacting Vmax, but instead by impacting the ability of the enzyme to bind to substrate. Activators let the substrate bind more tightly. Inhibitors make the substrate bind a lot more weakly. That's the way this works. Okay? Anybody remember what kind of inhibition that was? You sure? Okay. Yeah, so allosteric, right? Allosteric, non-competitive inhibition. Okay, so the idea here, and this is just to kind of demonstrate how this works, is what I'm showing here is two structures of the enzyme. The same enzyme, one of them has, the blue line here has ATP bound to the allosteric site. So this inhibits enzyme activity. We just saw that it inhibits enzyme activity by decreasing the ability of the enzyme to bind substrate. And the way that it does that is it triggers a structural change which moves a couple of these critical loops. And one of the loop changes puts this glutamic acid, which originally was interacting with carbon 3 and carbon 4 of fructose, and instead it shifts it so that it is literally physically in the space and preventing our substrate from binding. So we have this giant steric clash now where this glutamic acid is in the way, our substrate can't bind. That's how it decreases the activity. That's how it decreases the ability of the enzyme to bind substrate, is it shifts the structure in a way that physically puts something in the way. All right, so moving on here now. So that's this idea, this theme of activating and inhibiting enzymes is a huge theme in metabolism, right? This is how we control flux through these pathways. For glycolysis, there are three key places, the three irreversible steps. The most important one is phosphofructokinase because it's the one that responds to any condition. Okay, we're also going to see that it's the place that responds to organismal signals. It's the place that responds to hormone signaling. And y'all are going to love that. Love it. Okay? All right, so another big theme that you really need to appreciate is the idea that cells need to be dynamic. They need to be versatile. They need to be able to quickly respond to changing dynamics, to changing conditions, right? And practically what this means is that all these metabolites and all these pathways are linked. So if we inhibit glycolysis, other things need to ramp up, right? Inhibiting flux through glycolysis means that those metabolites have to be able to shift to do other things. If we activate glycolysis, then perhaps those other things aren't going to happen, right? It's all about thinking about the flow, the movement of metabolites through these pathways, okay? And just to kind of give you a sense of how some of these things are linked to glycolysis. And this is by no means everything linked to glycolysis. Glycolysis is central. These metabolites are central to all life, right? So we see here in the middle glycolysis, and we see that glucose 1-phosphate is linked to glycogen metabolism. This is the source for branching off and making glycogen to store energy, and it's linked to when glycogen breaks down. It's where the glucose enters into glycolysis. So stored energy breaks down and feeds into glycolysis. To store energy, we also need to branch off glycolysis and build up glycogen. Okay, we see that glycogen metabolism is linked to other places in glycolysis. Something else that we haven't talked about yet, but we will later on, is the pentose phosphate pathway. This is how we produce NADPH. It's also the starting point for the biosynthesis of nucleic acids. This ribose 5-phosphate is where DNA and RNA synthesis starts, nucleic acid synthesis starts, okay? And everything in the pentose phosphate pathway is dependent on branching off of a couple of the metabolites of glycolysis. Further down here, our 3-phosphoglycerate is linked to the biosynthesis or the degradation of several amino acids. So the idea here is that these pathways are linked, and flux through one pathway can dramatically impact flux through other pathways. They have to be linked, and they have to be controlled in a very thoughtful way. All right, so gluconeogenesis is the reverse of glycolysis. Okay, as the name suggests, it is the synthesis, the creation of new glucose. Okay, and the only way that new glucose is made is by reversing glycolysis. Okay, so if we think about what we need to do to reverse glycolysis, we have to overcome the exergonic steps, right? The three irreversible, the three irreversible steps of glycolysis are the three kinase steps we talked about before: hexokinase, phosphofructokinase, and pyruvate kinase. These are irreversible steps that we have to overcome if we want to reverse glycolysis. Okay, so two of these are actually fairly straightforward, but the third one is not quite as straightforward. So if we think just about hexokinase, right, we know that hexokinase catalyzes the phosphorylation of glucose using ATP as the phosphate source. Okay, we have the energy of each of these reactions. Glucose phosphorylation is characterized by a free energy change of 13.8 kilojoules per mole. ATP hydrolysis is characterized by a free energy change of negative 30.5. And overall, when you couple them together, it's spontaneous. Okay? We need to be able to reverse this for gluconeogenesis. To make new glucose, we have to be able to convert glucose 6-phosphate to glucose. Same thing goes for phosphofructokinase. We have to be able to convert fructose 1,6-bisphosphate into fructose 6-phosphate. Think about those two reactions, question 1 of your activity, and see if you can propose a way that energetically we can make this work.